Hello, welcome to ZenView Studios Lab, a new video about Triacs testing and calculating gate resistance and some small things you ought to know on Triacs to make your life simpler if you want to use those parts. Voila, let's go about it. All right, this is a video about Triacs. As you can see, there are three terminals in a triac, one of which is a gate. The other two are anodes, 1 and 2. There's a distinction between anode 1 and anode 2. Anode 1 is connected to the gate somehow. So when you measure, you will see a diode voltage between gate and anode 1 in both directions because it's a double junction. However, you won't get anything between A2 and A1. That's the normal condition for a triac. So if you test it, you can test it with a multimeter, is what I'm saying in other words, very simply. However, there's some things that multimeter won't tell you, whether it will tell you apparently whether it works or not. If you want to make sure, you can use two circuits. One of is with AC, which I won't show you here. Another one which I find simpler because it's using a power supply. I will show you the test directly on the power supply. Any bench power supply that supplies like 12 volts, but it can be 10 volts if it's whatever. Your only thing you need is a load to make sure that the triac will stay open when you switch it on. Let me explain. With AC, you make as long as you shorten the gate through a resistance that controls the current to A2, you get the triac to be conducting, meaning that it's like a closed relay. With DC, just an impulsion, if the current is enough, will keep the triac running and closed. This is why it's no good for DC, because the only way to turn off a triac will be by cutting the power supply. So obviously that's not a very good solution. But however, that's a very good, an easy solution with no dangerous voltages, since this is normally used with AC sources, which are maybe 220 volts or 120 volts plus the RMS calculation. Anyway, it's dangerous voltages. A simpler way to test your triac is, as long as you have some kind of resistance, and for some people like me working in audio, to 8 ohms, i.e. to in series, which is the 16 ohm here that you see, will do perfectly. And that's a dummy load I have. So this is what I use. And this way you can make a very simple circuit. What I show you here in this part is that you can calculate the resistance that you need for the gate, and this is the important thing that you ought to know. No matter whether you have a mock circuit, which is, we'll go over it a little bit later, it's a driver circuit, which is a opto-isolator or not, you will need to put a resistor here. The voltage, the gate voltage between the anode 2 and gate is normally, and you look at the spec sheet that you have, but for this BTA 24 that I use, it's between 0.2 volts and 1.3 volts. So that means like 0.9 or something like this, 900 millivolts will do perfectly. That's just to give you an order of idea. So this is what you should have. If you put a multimeter between those two pins, that's what you should read so that the triac switches on. Other thing is that the current that's going to flow is very often either 35 or 50 milliamp. Here it's a 50 milliamp triac, but I made just to show you how you calculate RG. It's very simple. You have your 12 volt, it's Ohm's law, minus the maximum 1.3 volts, and you divide it by the current, and then you get the ohm resistance. That's 306 here, that you should have here. That's the 306 or 350, 310 regular value will do, and it will protect the gate from being with an overcurrent. The same thing applies if you are doing AC, and this is the interesting thing. In the circuit that we saw with the pump, the AC is 30 volt, and the RMS value of that is 42.42, so it's by by a square root of 2, 1.414 multiplied. So you have the 42.42 minus 1.3, always the same, divided this time by 50 milliamp. This means that the gate resistance should be 820 ohms. That was a bit more than the resistance that I had in the circuit. But the interesting part is that this way you know and how to figure the gate resistance very simply. All you have to remember, it's the voltage that you're using minus the maximum 1.3 volts, and this way you can calculate with the divided by the milliamp rating of the gate that you have, and this way you get some kind of safe value. When I measured in circuit, I saw that my gate voltage was 0.9, which is perfectly fine in between the two boundaries and within the limits. So this is with a value which was a bit more. I used a 1K, I think, value rather than the 822. And this is a safe way to build the circuit. This is interesting because this is very often not clearly explained, namely that all you need to do is to have the supply voltage minus the maximum gate voltage that you get from the spec sheet, and this way you can get with Ohm's law directly the resistor, the gate resistor. One other thing that's very often not specified and explained clearly is that, and this is why I showed the DC circuit I'll show you on power supply, if you don't have a minimum current flowing through this, meaning instead of a load resistor you put a LED with a 1K or 4K resistor, you will not have enough current for this to be continuous, meaning it will give you the impression that because as soon as you open the switch, then the triac will stop flowing. That's not the real life story. That's because the load that you're using is drawing not enough current for the gate, for the triac to remain open. Under DC condition and normal, here in this case you have 750 milliamp, Ohm's law divided by 16 ohm, that's 750 milliamp, and that's enough for the triac, and I will show you that on the power supply directly, to remain open. In this case, no matter what you do, once you have made the short and made the triac conduct, until you close and you turn off the power supply, the triac will conduct. So this is why it's not useful in DC condition. With this, you cover all the interesting facts about a triac and what you ought to know. And this calculation gives you the formula to always safely figure the value for the gate resistor, which you should always use. It's better this way, you protect your triacs. And then I'll go over why this value doesn't have to change when you put a Mach. Because a Mach, now let's have a look at the circuit here. This is what I drew backward from the system with the pump, and the Mach is really a photodiode and a phototriac here. And what happens is it's making a short when the photodiode conducts. So in fact, this is like it doesn't exist. It's 0 ohm if you measure between the two terminals. It's just shorted, and therefore you can safely calculate your gate resistance using that formula. It's the same, whether you have 220 volts or in my case 30 volt AC. So that was a little rundown on Triacs and how to use them and calculate them. Some of the little things that are not, in my opinion, always explained clearly on videos on how to test and use Triacs. Voila. All right, testing Triac with bench power supply. The power supply is set to 12 volts, and we have the Triac here. And what you can see is you have one anode going to the minus, another one going to the plus, and the plus it's going through little dummy load that I have on the floor here. It's two 8-ohm resistors, big ones. This allows you to make some current run through the Triacs without problem. Okay, the way it works is fairly simple. The schematic you have already, and what you ought to do is simply put some current here up if it's in front of the gate. So one more time, very simply, all you have to do is touch the plus with the gate, and you see your current now is up, and it's staying there even though it's disconnected. And the only way to get it off is to turn off the power supply, turn it back on, and you see no more amps. If you do it again, up, you get, this means the Triac is working fine. It's conducting current, and this is exactly what I showed in the equation. You have a half of 1.5 amps, so 7,500 milliamps is what you got. Okay, that's very simple. 12 volts, all you need. And this way you can check that your little component there is working fine. And obviously you have, as I said, A1, A2 here, and the gate here. That's what you get from the spec sheet directly. Okay? Now we'll see it with the multimeter, which is the usual way people test without the bench power supply. That's a easy and safe way to do it, because with 12 volts you don't risk anything. All right, here we go again with the Triac. All you have to do is, this is in diode mode. Okay. And you see directly A1 to gate, one way or the other. A1 to gate, same thing. And between A1 or A2 and gate, or A1 and A2, you get nothing. That's and you can put a jumper. The only important thing is, the most important thing is that you get those diode voltages here, both direction. This means the Triac is functioning properly. Okay? And the way, so you can see the way I do it, one way. Always very simple. This tells you the Triac is functional. That's what you find in most videos. You can find with a jumper between A2 and the gate. It's in fact always showing the same diode voltage. And the only other thing which can happen wrong is that the A1 and A2 are shorted all the time. That means the part is no good. But here it's not the case. Again, if you put A1 on A2, you see there is absolutely nothing happening. Voila, that's it for the Triac with all the calculation. All right, I hope this video was informative. It's short, but to the point, and I think to the main points as to how to get a handle on Triacs, using them and calculating the resistance for the gate, which is quite important, obviously, if you don't want to blow them, and testing them safely without AC. You can do obviously quite safe with low voltage AC test. The only thing is that I figure that it's and it's the same for me, much simpler with a DC power supply, which you have very often on the hand, compared to AC, where you have to find a transformer, etc. I mean, it's a bit more complicated to put together to test. That's for now. I hope you enjoyed, and please do click the like button if you did. Thank you for watching.